problem is only for titration. We have, I think the problem states how many solute. So the problem asks for the number of solute in terms of millimoles. Um, so that's what we're trying to find. The number of solute of millimoles in 256 liters of 47.5 ppm. So this will be your concentration in terms of parts per million. Solution of magnesium nitrate. So we're trying to look for that solute. So magnesium nitrate in, of course, water. When the solvent is not even, it is usually water. So don't be surprised, because if you have samples in natural environments like your seawater, it's again water, with, of course, with minerals added as it. Anyway, you have 47.5 parts per million, and you just wanted to find how many solutes are there. So usually we notify number of moles in terms of N. So I'll be notifying it in terms of N. Okay? So I'm trying to find the number of magnesium nitrate. This one will be the solute in 2.56 liters of water. So one thing really to think when you have ppm is that parts per million. If you can see the definition of your parts per million, that is the number of grams in terms of a 1 million gram of a solution. So basically, that is to dilute. So meaning, as if you have a solution as if it only contains water. So meaning, why do we need this? Because we need the density to convert mass into volume. This is because, as you can see, we have a volume of solution. So we need that information, the density of water, for us to interconvert from mass to volume. So you only have to think of 47.5 as masses. That is, if we try to define it, it would be 47.5 grams. So that's what the parts per million says. Grams of magnesium nitrate in 1 times 10 to the 6 grams of solution. Okay? So this is the parts per million that is stated in a different manner, so that it will be easy. Actually, we can use the formula for ppm, but I think this would be the easiest one. I'll try to solve it in terms of the formula that I gave you. I think it is posted at the top, maybe. So as a first type of solution, I'll try this route. Okay. So this is parts per 1 million. This is ppm. 47.5 grams of magnesium nitrate in 1 million grams of solution. And then, you try to convert this one with, of course, the density. Again, your density will now act as if it is just a conversion factor. Okay? So that would be 1 gram of a solution for every 1 times 10 to the negative 3 liters of solution. So this is your density actually. Your density of your water is 1 gram per ml. So that's the density of your water. We notify density in terms of rho, the Greek letter rho. So actually, sir, where did you get that density? Density is already part of your chapter 1, wherein when you don't know the density actually, basically, you have to find tables. But you have to be suspicious enough that if you're trying to look for the density, maybe you're just trying to look for the density of water, and the density of your water will always be, by default, 1 gram per ml. Of course, your density fluctuates with respect to your temperature and pressure. But for your dilute solutions, just like this, if that is a sample from a river or from seawater, actually it changes not that much, but we could safely assume that it is near 1 gram per ml. So this is it. So we use the density as a conversion factor. So by that, we can already cancel off the grams of solution. Now, as you can see, our only problem now is, we have two problems still. The grams, we can convert that grams if we try to use a formula weight. Ano ya, bangin na parang mata. Okay, still running. So we can, this problem here, we can of course use a periodic table to find the mass per mole of your magnesium nitrate. And for this problem here, of course, we only have to plug how much volume did we try, where to find that solute is. So we just have to plug that one, 2.56 liters of a magnesium nitrate solution. Of course, the magnesium nitrate is the solute. So this would be cancelled off, and now our only problem now is to convert that grams into millimoles, and we resort to a formula weight. So you can look at your periodic table. Of course, we can always compute. I have here formula weights. Magnesium nitrate is Mg. So what I did, so we basically go to the periodic table and look for the masses. So I have a periodic table out there. So magnesium would be (24,305). So magnesium has a mass of 24,305, 24.305. So and then you have how many nitrogen? You have 2 nitrogen, since it is enclosed in a parenthesis. So your nitrogen is 14.011 times 2, and then added by how many oxygen do you have? You have 6 oxygen per atom. So that would be 6 times your oxygen weighs 15.999 grams per mole. So that would be 15.999 grams per mole. By that you have 148.3 to 1. So the formula weight of this one would be 148.3 to 1. As I said, not all formula weight is listed on the table that I gave you. So you really have to know how to get that one freshly from your periodic table, of course. Then we plug that one to our problem. So as you can see, the units of this one is gram per mole. So we need the grams at the bottom, so we interconvert. Because again, your conversion factor is always equal to 1. So we can just flip it over. So the 1 for. So I'll be giving you a second solution for this one, so that you can see what I am telling you. So again, this is a plug and check-in method. You don't have to be afraid actually. But for plug and chug, you really have to know, of course, the definitions of your density and your concentrations for you to be confidently using the plug and chug. But you can do it actually by practicing. If you don't like the plug and chug, I'll be offering you another method, where in case we will be plugging formulas. This would be like mathematics. So first, I have here the definition of your parts per million. The definition of your parts per million is it would be the mass of your X. I will be referring the solute as X. The mass of solute over the mass of solution multiplied by 1 times 10 to the 6. Of course, then the unit will come as ppm. So that's the unit that I gave you. So here, there would be the units here. Okay? The ppm. This is the concentration in terms of ppm. So when you try to use this one, why did I try to use this one? Maybe that's one of your first question. Then it will you should be using that one, or maybe you can use other things. You may not start from this one, but this is how I look at it. Since the given is since there is a given of parts per million, then you have to plug that one as the formula. Diba? And then other formulas, of course, will come in as you try to find that number of millimoles. So this one is already given. So usually, I put check marks on the things that already given. How about for the mass of the solute? It is not given. But what is given is this one is the volume of solution. This one is the mass of solution. So again, this is also not given. So we have to get this one from the density of solution. So these two are not given, meaning we have to find another expression that will probably replace that one. For your mass absolute, you need, of course, we've already seen that we need the formula weight. The formula weight actually is the mass of that species X per number of mole N. Per number of mole N. X. So maybe we can try to plug that one and substitute it with Mx. Mx now would be Nx times Fw. So that would be the number of moles multiplied by your formula weight, of course. So we will replace this one with Nx times formula weight. So by replacing that one, we would know now that this is what we're trying to find, the number of absolute X, and this is what we need. Since it is not given from the problem, again, as I'm telling you, there are problems there really that they won't be providing the formula weights. That's why we computed it to be 148.3 to 1 from the periodic table. So now we already know this one, since we have already seen it from the, in fact, this is an alternate solution for this one. How about for this one? We have also seen that density must also be a culprit in changing this one. So what's your definition of your density? Again, your definition of your density is that mass of the solution, because we're talking about the density of the solution, so that would be the mass of the solution with respect to the volume of solution. So that's actually your density. Meaning we can find this one by just incorporating a mass of solution would just be equal to the density multiplied by volume of solution. So this is just a simple algebra. So kung di ka maaari magsuga din then maybe you really have to question kaya nung ipasar ka mo ng algebra. Meaning, I don't have time to go back to that subject because it's really you. Diba? Kumari kami ito mag-develop. In fact, nalilipay pa kami makapasar. Kahit ba't ka nagmahulog? Ay, dito na padayan. So you only have to replace this one with the density of the solution and then your volume of solution. Wherein it is already given. So this is already checked because you can, this is always 1 gram per ml, maliban na lang kung if the volume, the density is given. But if it is not, you can assume that that is a dilute solution. So the volume of solution is already given, check. So this is already given because that's from the formula. So therefore, you can already find the Nx. So therefore, we can already use this one. Again, simple algebra. We can see that Nx would be equal now to CppM, of course, then the density of the solution, then multiplied by the volume of the solution, then divided by any radius. So the formula weight multiplied by 1 times 10 to the 6. Okay, and then unit would be ppm, the unit ppm, and then we plug the values. So CppM is already given, that is 47.5 ppm. Then you have the density of the solution, which is 1 gram per ml. Okay, and then the volume of the solution to be 2.56 liters. Just plug it all muna. Mamaya ka naman problema ng iba. So you have there, and then the formula weight would be 148.321 gram per mole. And then next is 1 times 10 to the 6 ppm. So by that, you can already cancel the ppm. What would be? This would be the gram of the mg. You're talking about the MgNaC, Mg magnesium nitrate, MgNO32. So this is also the magnesium NO32. But again, for this to work, you have to understand what you're writing. This is maybe you will be trying to plug in different substances. So you you must not do that because magsasayip gihapon tuya kundi ka masyadong nakakainit. But ini, it approach niya is mathematical. Okay? So this would be already be cancelled. And then, how about this one, milli and liters? You can now put your conversion factor which is 1000 ml. 1000 ml is 1 liter. So by that, I can already cancel that off. And then this one also can be cancelled that off. Conversion factor of 1000 ml is 1 liter. And then, now you have a unit of millimole. I mean, mole. Kaya di man niya ubusan-ubos, makatutiyay baw. Okay? So if you try to gather that, you would have numbers at the top, 47.5, and then times 1, pwede din mo surat, 2.56. This one is at the top, so you can write it down as 1,000. And then at the bottom, you have 148.321. And then you have times 1 times 10 to the 6. So the unit now would be mole of MgNO3 2. So as you can see, pareho na radio. So nag-differential na lang yung rahan. Anyway, you can get your calculator. Pero dapat talaga magpareho tira. 47.5 and then you have times 2.56 times 1,000 then divided by 148.321 times 1 exponent 6. By that you would have 8.20 times 10 to the negative 4. But again, your unit now is mole. MgNO3 2. So, kung karoy mo millimole, so ito 8.20 times 10 to the negative 1.